is Karaman from Aarhus University. I'm currently a postdoc working mainly on statistical genetics and try to develop new methods for genomic prediction. And currently it is genomic prediction of purebreds and crossbreds altogether. And thanks, Mons, setting up the floor. So I can just skip and move directly to the modeling part, which I like more. The more straightforward way to evaluate all purebreds and crossbred animals together is to use breed proportions. And this has been done before in Nordic red dairy cattle, where they showed an improvement of taking into account the breed proportions improves accuracy over a model which doesn't. And also it was applied in Danish Jersey, but Danish Jersey is not a mixture of two breeds, it's more like a mixture of two populations, US Jersey and Danish Jersey. And there was not really an advantage of having or taking into account these breed proportions. A recent study also uses, a recent study from US also uses crossbred information. They basically estimate breeding values for each population and then weight these breeding values with the breed proportions. But in all cases, actually, the first problem is that they rely on a genome-wide breed proportion. And if you just pick two individuals with the same exact genome-wide breed proportion, they may have a very different admixture pattern over the genome, depending on which chromosomal region is coming from which breed. So we hypothesize that this is not really the optimum way. And if we take into account the breed origin of the segment, so let's say breed origin of the alleles, as was done in pigs and poultry before for simple two-way crosses, we can have improved accuracies for both purebreds and crossbreds. So I will just move to the models before I give details about the studies we've done. So for within a cross and multi-breed prediction, we can consider this simple linear model where XB stands for the breed proportion part. So this is basically very similar to simply using breed proportions in a standard linear model. Also, we came up with a model which accounts for breed origin of alleles. I will give more details about these models later on, but in this model, we had two basic assumptions, which states that SNP effects are uncorrelated or SNP effects are correlated for the breeds involved in evaluation. So if you look at the first model, I said this is the part where breed proportions come into play, but of course this doesn't exist within breed or across breed predictions. This only exists if you want to use data from crossbred individuals. And for this, we partitioned the genotype matrices and the SNP effects into some subvectors so that we assign priors to all these subvectors instead of the whole genome. So that means we allowed genetic variants to differ over the genome. For the model that we came up with, we also did the same splitting of the genome into chromosomal segments so that we split it all these, maybe I should first mention what are these components here. Each of these M matrices is breed-specific components. So if we have an individual which is Holstein, then all the entries are here, but we have just zeros at this part. If an individual is a cross of, for instance, Holstein and Red, then that means we have entries in this matrix and here, and everything here is zeros. So we just counted the number of reference alleles that come from a specific breed for a crossbred individual. And this partitioning here also allowed us to have different variances over the genome separately for each of these pure breeds. This means we also allowed genetic variants differ for each of these for the breeds we have. And this setting, this prior setting we have here states that the SNP effects are breeds. We have the chance to enhance the data we can use, because if you just use data from a single breed, you have buttons. We also assign priors such that the marker effects are breed-specific, but yet they are correlated. We also assign priors to the genome regions again, so we allowed genetic or genomic covariance vary over the genome, because there may be higher correlation where the LD phase is consistent across the breeds. And there are some details about the priors we assigned to the models. I just skipped that. And we tested the approach with a simulation study starting from real data of 3 dairy breeds, namely Danish Holstein, Swedish Red, and Danish Jersey. We picked about 1,000 individuals from Holstein and Red, and we wanted Jersey to represent the small breed, so we selected a lower number of individuals from the Jersey population, and we did simulations for 9 generations for both pure breeds and admixed individuals. For the admixed individuals, we started simulations with mating Jersey males and Holstein females, and then we continued with Red, Holstein, and Jersey in turn until we reach 9 generations. So each time for the admixed individuals, each time we used purebred sires and crossbred dams from the admixed individuals from the previous generation. Starting from the same set of real data, we simulated 10 different data sets, so we had 10 replicates. We limited ourselves to use only the first 5 chromosomes just for computational reasons, and because we had a lot of scenarios and replicates and so on. So from there, we picked 250 QTL, and we picked those QTLs with the assumption that they have relatively low minor allele frequency compared to SNPs. So we applied a criterion here. So we, on average, we had QTL around 0.15 and SNPs around 0.20, 22 for each of these breeds. And we directly simulated QTL effects from different correlation scenarios, namely 1.5 and 0.25. One means that they exactly have the same SNP effects for each of these breeds. And breeding values we simulated simply multiplying the allele content by the QTL effect we simulated for a specific breed. And we had 2 traits representing a high and a low heritability trait. For each trait, we did separate analysis, and we used a full cycle, which is generation 6, 7, and 8 as reference, and generation 9 as validation. And when we did that, we had, so since we have 1,050 individuals from each of these breeds, in total we had 3,150 from each of these breeds to be used in the reference, and 660 from Jersey to be used in the reference population. We followed 3 different strategies to use the information we have. So we could, we can say they are classified as pure, combined, and POA, which is breed origin of alleles. So pure models, we only use the data from a single pure breed to estimate the SNP effects. In the combined analysis, we combined the data of the pure breeds, or also data of the pure breeds plus the admixed individuals, as if it's just a 4th breed, it's a different breed. In the breed origin of allele models, we took into account the breed origin of allele for all these individuals, and as I just explained, we had 2 scenarios where we assumed that the SNP effects are uncorrelated, or either they are correlated. And in the validation population, we had 1,050 from each of Holstein red and admixed populations, and 220 from the Jersey population, which again is a small breed. And we, to consider different variance covariance structure over the genome, we had different region sizes or genomic segment sizes. We applied from one SNP to whole genome. 100 SNPs are just picked randomly to show if there's an advantage of grouping SNPs, which we have observed before, but it doesn't mean that 100 SNPs is the optimum one. It's just something I picked. And if you want to relate these methods to some existing or well-known methods, the one SNP in this case can be seen as an extension of a regular base A to multi-breed scenario, and the whole genome can be seen as an extension of a SNP blob or a G blob to a multi-breed scenario. I first looked at if this if region size has an impact on the accuracy, and combining the accuracies from two traits, one thing I can conclude is that the whole genome gave us the lowest accuracy overall, but there was no difference between one SNP and 100 SNPs. It may just be because 100 SNPs is just, you know, picked randomly or arbitrarily, I would say. So I will continue by sharing the results from one SNP scenario. If we look at the small breed, which is Jersey here, we can see that in all these scenarios of QTL effect correlations, a crossbreed prediction using SNP effects from Holstein or red gave us very low accuracies, and it gets lower as the QTL effects, actually, the QTL effect correlations gets lower, so the QTL effects becomes more different. And for this small population, apart from the case where the QTL effects are identical, there was really no benefit, or even it decreased the accuracy by using all available data from the pure breeds. So when we combine data from Holstein red and Jersey, we can see that it gave us a lower accuracies than using only Jersey breed, depending on the QTL effect correlation. But if you look at here, there's actually little or no benefit, even when the QTL effects are identical. But when we add data from admixed individuals, just as it is a different breed, as a fourth breed, then we get higher accuracies, higher than using all pure breed data, or higher than using even the breed itself. And when we took into account the breed origin of alleles, we further improved the accuracies for this small breed. And it's more apparent if the correlations between the genetic correlations or genomic correlations reduces between the breeds. It's the same for the same trend for the low heritability trait. So I will just skip this here. And if we look at the large breed, which is Holstein in our case, again, what we see is that a crossbreed prediction, I mean, using SNP effects from one pure breed to get the breeding values for another breed. So if we look at here, we see that the crossbreed prediction gives us very low accuracies, even as low as 0. In this case, adding other pure breeds in the reference population didn't really increase or even decrease the accuracies, maybe less apparent than we observed in Jersey, but yet it doesn't really add any information. And when we add data from admixed individuals, the best we could have is we reach the accuracy we have with the Holstein population. And that wasn't the case for Jersey, maybe because, I mean, it's not maybe, it's most likely because in Jersey we had a smaller reference population, which needed more data. But for Jersey, we had a very large reference population, and adding more data didn't really help. And in this case, even for this large breed, accounting for breed origin of alleles also improved accuracies compared to single breed evaluation or compared to all other scenarios, combining all available data and so on. And also it's the same trend for a low heritability trait as well. If we look at the admixed population, one thing we see here is that they represent kind of the recent relationships, because we use generation 9, for which the sires are from Holstein population, and then run sires from the red population. So the accuracies by using SNP effects from one single pure breed reflected the recent relationships from these pure breeds. We also applied another, maybe one of the common ways of estimating breeding values for crossbreds. We estimated SNP effects separately in each pure breed, but accounted for breed origin of alleles in the candidates. And this gave us higher accuracies than using any of these single breeds. When we added data from, when we used data, or when we combined data from the pure breeds, then we also got high accuracies, but that is limited to only the scenario where we have identical SNP effects. In other scenarios, we actually had lower accuracies than the scenario where we had estimated the SNP effects separately in the pure breeds, but account the breed origin of alleles for the candidates. But when we added the data from admixed individuals, this picture also changed, so that we reach very high accuracy for in all scenarios for these admixed individuals. And maybe a very good thing for us that when we accounted for breed origin of alleles, the accuracies improved like 10 percentage points. So we jumped from like 0.8 to 0.9. And this is of course more apparent if the breeds become the breeds become less related. So it makes more sense to account for breed origin of alleles. And the same trend for low heritability trait. So to conclude the results from the simulation study, it shows us that if we combine all pure breed and admixed population data, we get an improvement for the accuracy of small breed. Also, if we consider breed origin of allele approach, we reach the highest accuracies. Of course, it depends on the scenario of QTL effect correlations. And in real data applications, there are some limitations, because you first have to decide which breeds to be included in the study, which can be very high number. Also, you have to estimate breed origin of alleles from the real data. Since we did simulations, we knew exactly where does these alleles come from each of the pure breeds we have. And these together may limit the accuracy of breed origin of allele methods we applied. But I know that there are methods on the way to estimate these breed origin of alleles accurately, also for more complex admixture. So I will also share some results from a real data. And here we have the red dairy cattle example. And these are the work done by a PhD student, Anna. Mons has mentioned more about her yesterday in his presentation. And Anna started with 50,000 RDC animals, and mostly cows. And we also have 5,000 bulls. And she split the data based on the birth date. So born after, also there were other criteria like relationships and family structures, but I'm not going to go in more detail. She separated the reference and validation populations based on the birth date. And in the reference, we had about 40,000 animals, and in the validation, we had about 11,000 animals. And If you want to apply breed origin of allele approach in real data, then there are some ways that you have to go. One is that you need to have a phased genotypes, which Anna did using fMpute. And then you have to decide, at least in this case, where admixture is more complex, then you have to decide which animals are pure, so that you have to estimate their breed origin of, you have to estimate the breed origin of alleles in the population for each individual using available softwares, for which Anna used admixture and chroma painter. So she first looked at, phased the genotypes, and then to be able to use the information also in the, because they had different number of SNPs in both data sets for Red and Holstein. She first, after phasing, she first picked up the ones that were fully phased, because otherwise we cannot use them, and then merged the two data sets based on the common SNPs. And in this SNPs, we had about 40,000, which comes from the 50K SNP chip, and also some whole genome selected SNPs, Danish and French SNPs, about 5,000. So in total, we had little less than 48,000 SNPs in the data set. The first thing after phasing the genotypes, the first thing is to decide which animals are pure, so that we can use them as donors to assign breed origin of alleles in the rest of the population. And she did some admixture analysis, and you can see the analysis results here. So we used only bulls here to decide, these purebred animals. But looking at here, you can see that we didn't really have a very large number of purebred animals, and it's very much admixed. Especially the Swedish animals are admixed with Finnish quite large. So we applied a threshold to decide purebred animals from each of these purebreeds. And here are the thresholds we applied for RDC and Holstein, and that led us this little less than 2,000 purebred animals, which were used to estimate breed origin of alleles for 51,000 animals in the whole data we have. And one problems we had with this estimation of breed origin of alleles, this could be this is, I think, most likely a population-specific case, because we didn't really have assignments with high probability. So only 40% of the alleles were assigned with a probability higher than 0.9 to a certain breed. So it was a little uncertain, which allele goes to which breed, or which allele belongs to which breed. So instead of using this assignments, in any case, Chroma Painter assigns these to, or you can use Chroma Painter output, because it gives you probabilities, and you can just assign them to a certain breed if you want. But instead, we choose to use probability. Each individual, we had the probabilities of which allele belong to which population. So in that M matrix, we had the probabilities for each breed. And she tried different scenarios. First, she followed the combined analysis, which is the current practice in red dairy cattle analysis. So she just assumed that it's a single homogeneous breed. So she just analyzed the data as a joint population. Also, she used the breed origin of allele models. We just discussed the results for simulations. And then she considered different region sizes, namely 1 SNP, 30 SNPs, 100 SNPs, and the whole genome. And also she wanted to see if we get an improvement from using this additional or whole genome selected SNPs on top of the 50K SNP chips when we when we use breed origin of allele models. And she also tested if correlated and uncorrelated effects gives different results. So first thing we can see from the analysis here is that region size of turtle SNPs gives us the highest accuracy across all other region sizes. So, and this yellow bar is the traditional, which is the combined analysis. The green bar here is the correlated analysis, and this blue one is the analysis assuming no correlation between the breeds. So actually in the current practice, even if they just go defining a region size of turtle SNPs over this whole genome analysis, they can get benefit. That's the first observation. And the second thing is that we can see here the no correlated analysis gave us the lowest accuracy. That is simply because this no correlated analysis uses roughly 1/3 of the information in the data. So it's just used the breed-specific information in the data. And when we assume that SNP effects are correlated, the best we could do is that we reach the accuracy of the joint analysis. And this is more likely a result. This is more likely a result of this breed itself, because it's been going for many generations. Like it's more like stabilized. And when we looked at the correlation between the SNP effects, they were as high as 1. So in this case, that's the worst case. I mean, for our model, that's the worst case, where you have the same SNP effects for all the breeds, so you can just combine them. But one good thing is that even in that case, our model is not worse than the joint analysis. So it's this is an extreme case where joint analysis makes more sense over this breed origin of analysis, and maybe it's not the best example to show the advantage of breed origin of allele models. The next steps, we consider to use the Irish data in collaboration with Bridget. She had already extracted some data and did some work on data cleaning and such. So we can try testing our models with Irish data where the breeds are well defined, not as in this RDC population. Also, Iola will test these methods in Procross data, and we also have a plan for Julie use simulations, maybe testing more practical scenarios where we do not use all the phenotypes from the pure breeds, but instead summary statistics from routine evaluations. And I had the chance to test this approach with a little loss of accuracy from the original full data analysis using breed origin of allele methods. We still get high accuracies, close to the original breed origin of allele analysis. So it's a promising way to combine all available information from pure breeds and crossbreds. And this is yeah, I hope we can get something until the next NOEL meeting. So thank you.